Welcome back, everyone. In this lecture, we're going to talk about histograms again, and we're going to continue our discussion with two additional topics. The first one being histograms on a masked portion of the image, and the second one being histogram equalization. As we mentioned in the previous lecture, we can actually select a specific region of interest and only calculate the color histogram of that masked section. We're going to show you how to create a mask and then achieve that effect. That should be just kind of a brief little overview of applying the mask and then calculating the color histogram. The larger part of this lecture is histogram equalization. And histogram equalization is a method of contrast adjustment based on the image's histogram. Previously, we saw how we could use gamma correction to increase or decrease the brightness of an image. Now we're going to show you how to increase or decrease the contrast of an image through histogram equalization. Here we have a little figure, and on the left it shows what the original histogram or color histogram of the image looks like, and we're essentially going to flatten it out or equalize it. And we're going to walk through an example of what that actually looks like. So here's an example of an original image. It's essentially just a bunch of grays. So on the left here we have the actual color values, and then in the middle we have just this small image. There's not really anything there, it's just a little white circle with lots of gray around it, and then we see the original color histogram. Something to note here is that the histogram for this original image, it doesn't have any values at 0 or 255. So it doesn't have anything that's pure white, and it also doesn't have anything that's pure black. What we're going to do is apply histogram equalization, which is going to reduce the color depth. And what we mean by reducing the color depth is you're actually reducing the shades of gray. Or if you're working with a particular color channel, then you're reducing the number of in-between colors between 0 and 255. So again, take a look at the original minimum and maximum values in this array. I've highlighted them here for you. Currently, the minimum value is 52, and the maximum value is 154. What we're going to do now is apply histogram equalization, and definitely check out the resource link in this lecture for the full mathematical breakdown of how this actually works. It works for a cumulative distribution function, but right now we're just concerned more of the effects of applying histogram equalization. So after you apply histogram equalization, notice what happens to those left values. That minimum value that was 52 now gets transformed to 0. And that max value, which was 154, then gets transformed to 255. And let's take a look at what happens to the actual image itself. So notice it's kind of just this blurry, almost gray, almost white circle there. And now it's clearly been high contrasted so that the circle in the middle is clearly now white, and then we have a clear border or edge. And the histogram is also now more flattened out. And now it extends all the way from the minimum possible value of 0 all the way to the maximum possible value of 255. So notice again how the min and max values have now been equalized to be 0 and 255. We also now see less shades of gray, so this results in a higher contrast. Let's see now the results on a normal image. So here we have a left-hand side image of just some hills with some trees on them, and then we have the actual histogram. So the red represents the histogram for those grayscale values, and then the black line represents the cumulative histogram there. And essentially what that does is it just keeps adding things up as you go towards the max possible value. And if you apply histogram equalization, what happens is the cumulative then becomes kind of this linear step function, and we get much higher contrast in the actual image. Again, we're going from something with low contrast, and if we apply histogram equalization, then we get something with high contrast. And we've also flattened out that histogram a bit. Keep in mind, we don't make the histogram perfectly flat. Instead, what we really focus on is making that cumulative process. So if we take the corresponding histogram in red versus the cumulative histogram in black, we take that cumulative histogram and make that much more linear than before. So that's the actual real process, and the mathematics behind histogram equalization really focus on that aspect, making that cumulative histogram much more linear. Okay, so let's explore these concepts with OpenCV. Let's open up the Jupyter Notebook. All right, here I am in the notebook from the previous lecture where we ended up calculating some color histograms for various images. I'm going to be starting off by using this rainbow image right here. So let me copy these two lines of code and come back down here, run those. So we've uploaded rainbow and show rainbow, and let's quickly check the shape. And in fact, let's reassign rainbow just so we don't mess around with it too much. We'll reassign it to image, and then let's check image shape. Okay, so we're dealing with 550 by 413 on 3 color channels. Now it's time to create a mask. So probably the easiest way to create a mask is just by using NumPy. We'll say mask is equal to np zeros and then check the image shape. And in this case, we're only concerned with the mask on the X and Y dimension. It's not like we're going to mask certain colors out. We just want this on the 2D plane, and then that mask will be extended to the 3 other channels. So in that case, we're only concerned with these first 2. So the shape is going to be :2. And if you take a look at this, what the actual result is, it's the same as the first 2 indices. So we have 550 and 413. So that's all this is. So it looks like a complicated command, but it's really just grabbing the X and Y components. And then next, we're going to have the mask be an 8-bit integer. And so if we take a look at our mask now, what we're going to do is reassign some of the points to be pure white. So remember right now, the mask is pure black. So if we were to say plt imshow the mask, it's a bunch of zeros, so it's pure black. And let me actually make the C map here gray so we can actually see that. So in grayscale, it's going to be completely black because they're all zeros. Now what I want to do is get a rectangle, kind of an arbitrary piece that you want to have as your region of interest, and that's what I'm going to choose as my mask. In that case, there's really no right or wrong answer as far as like what should be masked and what shouldn't be masked. That's up to you. But what we could do is take our mask and let's just take a slice of it. We'll go from 300 to 400, and then we'll say from 100 to 400. So we're taking a slice about 100 pixels along this direction, so from 300 to 400 over here on Y, and then from 100 to 400, so this block over here, so most of the x-axis there. And I'm going to reset those all equal to 255, so they're all white. And then once I've done that, let's show the results. We'll say mask, and then say CMap gray. And now you'll notice that from 300 to 400 on the Y, and from 100 to 400, now I have an area that has been masked off. And we've already seen masks a little bit with bitwise and then bitwise OR operations. And we're going to be using those same operations to essentially filter through, just on the white space, the original rainbow image. So remember, the rainbow image, if we say imshow image, this is the rainbow image. And it's actually kind of incorrect the way I'm showing it right now. I should be showing you show rainbow. There we go. So this is the color corrected. What we're going to be doing is we're going to be masking that image. So let's comment this out and then create a masked version of that image by saying masked image is equal to CV2 bitwise and we're going to pass in the image twice and then say mask is equal to the mask we created. So that is the masked image, and we're also going to create a version of show masked image. So we'll say show masked image is equal to CV2 bitwise and then we're going to pass in show rainbow twice and then pass in the mask. Okay, so again, the reason I'm doing both a masked image and a show masked image is this one is purely for visualization purposes. That way I can visually see the correct red, green, and blue color channeling order. This one on the masked image, that's for the actual histogram calculation. Okay, so let's display what the actual image now looks like with our show masked image. And there we have it. So now I'm only seeing this portion of the rainbow. Notice now how this portion of the rainbow doesn't appear to have that much red compared to the original image. So we should expect that our color histogram also reflects that. Let's calculate now the histogram masked values. We'll say histogram mask underscore values, and we're going to just calculate on the red channel. So we'll say CV2 calc hist. And the way this works is as a list, you're going to actually pass in the original image. So we're going to pass in rainbow. And then the channel we're looking for is the red channel, which in this case, since OpenCV, remember its default is blue, green, red, that means red is at index 2. So we'll say channels is equal to 2. And then we'll say mask is equal to the mask we created, which remember is up here. This is the actual mask object. Okay, so then we have the mask we created, and then the other parameters we're going to say are the hist size and ranges. So those are going to be the same as before. We'll say hist size is equal to 256, and then, ranges is equal to 0 to 256. Okay, so a lot going on there, but we'll go ahead and run that. And let's do one more for good measure. However, this time, we won't apply the mask. So we'll say just hist values red. So I'm going to delete that, and we'll set mask equal to none, just for comparison's sake. So let's run that, and now let's actually plot these out. We're going to say plt plot, and we're going to start off with hist mask values red, and I'm going to title this, just so we can understand what we're looking at. This is the red histogram for masked rainbow. And what does the actual masked rainbow looks like? Well, it looks like what we have up here. Notice there's not a whole lot of red going on. So let's actually run this and see what it looks like. Okay, so you'll notice, just as we predicted in this red histogram, there are very low values for red, and most of the values are actually 0. And then as we continue going on, we see less and less pure red value. So not a whole lot of red going on there. Now let's check out what happens if we were to do the same thing for the full rainbow image. Remember the full rainbow image, if we actually display it, let me just display it quickly here. PLT imshow, show rainbow. Remember, this one actually has quite a bit of red, including representation here in the purple area and violet area. So we're going to do the exact same thing. We're going to PLT plot, except in this case, we'll do the no mask values red, and then we'll say for normal rainbow. And if we run that, notice now we see way more red over here. So we're pretty much doing the exact opposite of the masked. And that's because we can see that much more of the image is actually represented through the red channel. And that's the basics of applying a mask to a histogram. So in general, we really won't be doing color histograms that often. And when we do color histograms, we probably won't be applying a mask to any particular area. But just in case you need to understand that, basically you can always just reference the code in the notebook on how to create a mask, which we've seen a little bit of before, and then how to actually just calculate it and then pass in that mask. And this step right here of mask image and show mask image, that was kind of just an in-between step so we could clearly see what was going on there. But really, all you need to do is create this mask right here, which is essentially just creating NP0 as black and then filling in your particular region of interest with white, and then you can create the mask that way. Okay, we're going to go ahead and now move on to the main part of this lecture, which is the histogram equalization. Remember, that's a way we can display contrast. So I'm going to create a couple more cells here, and I'm going to upload a new image that we haven't actually seen yet, and it's an image of a gorilla. We'll say CV2, imread, and inside your data folder, wherever you happen to have it, we're going to upload gorilla JPEG, and we're going to upload it as a grayscale. And let me also just get the display function working. I'm going to copy and paste the display function from the notebook. Again, this is the display function we've always been working with, display image or display. So I'm going to run that, and let's display the gorilla. So we'll display gorilla, run that, and actually let me clarify the CMAP is equal to gray. Run that. And so here we have this picture of a gorilla. It's quite a large image. If we actually check out the gorilla shape, it's about 1300 by 2000, more or less. So what we're going to do now is calculate the histogram, and then we will equalize the histogram and visualize the difference. And then we'll run this again on the color version of this image. So let's first do this in black and white. What I'm going to do is just calculate the histogram values here. We will say hist values is for the gorilla image is CV2. Calculate hist. Say gorilla. Channels 0. Because we're just focused on one channel, it only has one channel, it's grayscale. We're not doing any mask, we'll say mask is none. Hist size is equal to 256, and then the range is equal to 0, 256. Okay, so, whoops, range is, there we go. Then the next step is to simply just plot out those values. So we will say plt plot hist underscore values, run that, and there we see the actual histogram. So here's the histogram on the grayscale image. Looks like we have a lot more kind of lighter colors and then a couple of darker colors, but not so much pure black. And if we take a look at the image, it looks like a big chunk of those lighter colors are from the rock behind this gorilla. And the gorilla itself is actually pretty light colored. There's nothing too dark or too black. Maybe a little bit around its fur and a little bit around here on the edge. But really we can see here, there's just that little spike of dark, but most of it seems to be a lighter gray. And I can tell just because this is a grayscale image. Now let's show you how we could equalize the histogram. So I'm going to make a version of this called equalized gorilla or EQ gorilla. And the command is actually really straightforward. It's just you call equalize hist, and I encourage you to tab autocomplete that, and then just pass in gorilla. And first off, let's just display what that result looks like. So I don't actually even need to calculate the color histogram to do this. I can straight up just call it on an image and then display the result. So notice just how much the contrast has been increased here. So when we equalize the histogram, we've definitely increased the contrast. Notice now that those light grays are essentially now the minimum value of 0, and those darker values kind of around the hair and fur and over here on the edge, those are now the max values of black. So compare these two images, we get a lot more color depth here in gray, and upon equalizing the histogram, now you see a much higher contrast. And if you wanted to, you could then calculate the hist values for the equalized gorilla and display the result. So let's go ahead and calculate that. I'm just going to copy and paste this command, except now I'll pass in the EQ gorilla. Run that, and whoops, make sure everything's okay. EQ underscore gorilla. There we go. And we'll say PLT plot hist values. And now notice the behavior you get. So you get these constant spikes down because there's 0 value there. But if we compare this to our original, it's definitely been more flattened out. So we can see here that we tend to kind of quickly decrease as we go past 50. And then if we come back down here, the decrease is much shallower as you go beyond 50. So it's a much shallower drop compared to the original image here, where it was a much quicker drop. Okay. So that's the difference, and really the effect is a higher contrast. And keep in mind, you can actually do this exact same thing for a color image. So the way we do that is first I'm going to read in the color gorilla. So I'll read in the image again, except this time I'm just going to read it in as a color image. We'll say cv2 imread data / gorilla. And if I want to show the gorilla, I'll create a show gorilla where it's converted to the correct color space. So we say cv2 color, pass in the color gorilla, and then say color underscore BGR to RGB. So let's display what the colored version of the gorilla looks like. We're going to say PLT. In fact, we can actually just use the display function we defined. We'll say display our show gorilla. So this is what the color version of that image looks like. So here's the gorilla, it's in full color. If we actually want to equalize the histogram of a color image, essentially increase the contrast of the color image, the way OpenCV works is you actually translate that first to an HSV color space. Remember, that's the hue saturation value. So I mentioned earlier, we really wouldn't be dealing too much with HSV. This is one of the few instances where we do, just because of the way the equalize histogram function works. So what we will do is create an HSV version of the gorilla. We'll say HSV is equal to CV2, and then change the color space of the original color gorilla that we read in. And we're going to change it from the default blue, green, red to hue saturation value. So we have this HSV version of the gorilla, and then what we're going to do is grab that value channel, because the value channel is really the one we're interested in. So we'll say HSV : and the 0 channel, that's the hue, the 1 channel, that's the saturation, and we're interested right now in the value channel. So this is going to be our value channel right here. And if you check out kind of the min and max values here, these are the ones that go from 255 to 0. So what we're going to do is we're going to equalize this value channel. So I will copy and paste right here, and then I'm going to set that equal to the results of CV2 equalize histogram of that particular channel. So I'm taking that value channel, equalizing that value channel, and then replacing the original values. So we're going to run that. And then what I'm going to do in order to display the results, I'm going to convert this HSV gorilla to the RGB that we're used to. So we will say the equalized version of the color gorilla is equal to CV2, CVT color, HSV, and then we're going to take that HSV and then convert it to color space from HSV to red, green, blue. And now I can display the equalized color gorilla. And now we see here much higher contrast than in the original color gorilla image. So if we come back up here, we have a lot more color depth. It seems to be a little darker. And then when you come around here, now notice the rock behind the gorilla is much brighter. And over here on the edges, it's much darker. So we increase the contrast. And we're able to do that simply by just isolating that value channel in the HSV, applying equalized hist, and replacing those original values with the equalized histogram version, and then converting it. This is just for display purposes to RGB. And then we have our high contrast gorilla. Okay. So in this lecture, we learned how to equalize histograms to create higher contrast images, as well as how to apply masks to only calculate the color histogram for a particular section of an image. That ends our discussion on histograms. We will see you at the next lecture.